Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our today's topic is low stress mechanical characteristics. We will discuss the analytical approaches of low stress mechanical characteristics of textile fabrics. So if you see the fabric handle, okay, the low stress mechanical characteristics is mainly important for apparel textiles and home textiles. Okay. Like for industrial fabric, performance characteristics are important, but for apparel textiles, the handle is important. So this is basically whether it's smooth or rough, stiff or lean, its draping quality. So all these aspects we will be discussing here in this session. So first low stress mechanical characteristic is bending. So bending is tested generally using cantilever principle. So a horizontal strip of fabric is allowed to bend like a cantilever under its own weight. Here in textile material, we don't apply any additional weight. On its own weight, we allow the fabric to bend. So this is suppose the platform, and here it's a fabric specimen blue color, and on the fabric specimen one standard scale is placed, and when the scale is moved along with the fabric specimen, the fabric, due to its flexibility, it will bend due to its mass. Okay, on its due to its own weight, it will try to bend, and then if we continue sliding it, the overhang length will increase. So when L is the length of overhang, then the tip of the fabric specimen is touching one in imaginary line which is theta degree below the horizontal plane. So depending on this length and depending on the bending characteristics, the length, the theta will change. Okay, so if we keep the theta constant, and depending on the fabric bending characteristics, this length will change. So by measuring the length, overhang length, we can, for a fixed theta value, we can calculate the bending characteristics. So from Peirce's empirical equation, the flexural rigidity, mass per unit area of fabric are related in this way, where length L is the length of overhang and theta is the angle which the fabric end point is making with the horizontal plane. So MLQ multiplied by cos theta by 2 divided 8 tan theta. This is the relationship C is the bending length, is the concept that we will discuss. C is related with the overhang length by this relationship, C equal to L multiplied by cos theta by 2 by 8 tan theta power 1/3. Okay. And if we try to solve this equation here for theta 7.1 degree, if we use theta 7.1 degree, the entire this component, that is cos theta by 2 by 8 tan theta, becomes 1. So in that condition, C will become L. C will equal to L only when theta becomes 7.1, that is cos theta by 2 by 8 tan theta. If we use theta equal to 7.1, so this value will be 1. It will be approximately 1. Now, what does it indicate? It indicates that when the tip of the fabric specimen is reaching one point which is 7.1 degree lower than the horizontal point, so it's making the angle 7.1 degree. At that point, the overhang length is equal to bending length. So bending length can be defined as the overhang length when the tip point is making angle 7.1 degree. So higher the bending length, steeper is the fabric. So bending length can be defined as the length of the rectangular strip of material which will bend under its own mass to an angle 7.1 degree. Okay. So to calculate the bending length C, if we develop one instrument which is 7.1 degree, in which the 7.1 degree is drawn just below the horizontal plane, then we can directly calculate the bending length by the overhang length directly. But the problem with textile fabric is that it's very flexible, and that's why the angle 7.1 degree is too low to identify the length L. So there will be error. So the next step is we have to find a particular angle from where we can get this factor as a very easily calculatable factor. Easy factor. So one is the simplest factor. So next factor should be 1 by 2.5 is another factor. So this 0.5 we can get if we solve this equation. We can get this factor 0.5. This is the total factor 0.5 when theta becomes 41 point. At that angle, we get this relationship C equal to 0.5 A. So ideally it should have been C equal to L, but the problem comes the angle 7.1 degree is the very small angle. So next is 41.5 degree, where the relationship becomes C equal to 0.5 L. So for our bending strength tester, like a Sarli stiffness testing machine, where we keep this angle as standard 41.5 degree. The Sarli stiffness tester works in the same principle. So the strip dimension is 200 millimeter by 25 millimeter. 25 millimeter is width, allowing the strip to bend to a fixed angle 41.5 degree under its own weight. The overhang length becomes twice the bending length. So the function was that factor was 0.5, C equal to 0.5 L. L will be 2 of bending length in that condition. So we can see here this factor becomes 0.5 when theta is 41.5 degree. So in this diagram, what we measure, we slide this scale, standard scale for the stiffness tester, fabric bending tester, and we can get reading of bending length in centimeter. C, bending length in centimeter. If we observe carefully this scale, it's not a normal scale, centimeter scale. Here scale is that here 1 centimeter of bending length, if we see, this will be actually it's 2 centimeter. But here in the scale it's shown directly 1 centimeter, 2 centimeter, 3 centimeter, but this is for bending length scale. It's not, it cannot be used for other measurement, other length measurement. So that's why it's a 2:1 ratio comes, which is related with the fixed angle 41.5 degree. If we can have imaginary one instrument where we keep 7.1 degree angle, in that case we can use the normal scale. So if the question comes that can we use the normal scale, well, yes, we can use the normal scale, but in that case in the tester our angle should be 7.1 degree instead of 41.5 degree. Okay. Now flexural rigidity G is given by this relationship as we have already seen. This is the ratio of small change in bending moment per unit width of the material to the corresponding small change in the curvature. And for unit conversion, we can get the bending flexural rigidity of textile by this relationship, where the G equal to M multiplied by C cube multiplied by 9.807 multiplied by 10 to the power minus 6 micronewton meter, where M is the mass per unit area of fabric, gram per square meter, and C is the bending length. Okay. And bending modulus is the stiffness of a fabric in bending is dependent on the thickness. So for the same fabric, if we increase the thickness, okay, the bending modulus will change. So thicker the fabric will be more and more stiffer. So bending modulus is independent of the dimension of the strip. So that's why if we divide the rigidity with the thickness, we will get the bending modulus, and given by this relationship 12 multiplied by G multiplied by 10Q divided by TQ, where T is the fabric thickness in millimeter, and bending modulus unit is Newton per meter square. Now, the Shirley stiffness tester can be used for relatively stiffer fabric, but for very flexible fabric like knitted fabric, thin knitted fabric, the Shirley stiffness tester cannot be used. So there we have different approaches for two lengthy fabric. These approaches are different loop type method. One is ring loop method. So this is the length of the fabric L, and if we form a loop ring form, circular ring form initially, and then after hanging, this loop will get deformed. This is the gripping point. So this is the deformed loop. So from there we will get the bending rigidity. So L is the strip length, L0 is the undistorted length of the loop, that is distance between the grip point and farthest point. So for a ring type loop, this is the gripping point, and here is the distance at the farthest point. So this is the distance L0, at L0, L is the L0, and L is the total length, the circumference of the circle, the ring. And after releasing, it will become deformed. This is the deformed portion, and where after hanging, due to their weight, the distance become L. So this is become L. So the deflection is L minus L0. the formation of loop is a ring, that's why it's called ring loop. Now we can change the formation. If the initial formation is in the form of peer, this is the peer formation, this is a gripping point, and for undistorted distance is this is the point here. L0 is the undistorted distance and total length is L, and as the material is flexible, so this loop will become distorted loop. So this distance becomes L. So here D will be again L minus L0. This is called peer loop because the initial shape is like peer. Another type of loop is heart loop. The loop is formed like a heart. Initial, this is the gripping point, and distance, maximum distance from the gripping point is L0, and after deformation it becomes like this. After deformation, this heart loop will become this. In that case, distance here, the deformed distance is L, so total deformation will be L minus L0, where initial total length of the loop is the L. So using these three types of loops, we have different relationship, and we can get the, so this is the peer loop. For peer loop, the relationship is different relationship we will get. This is for peer loop, ring loop, and for heart loop, we have different relationship. This is the relationship for heart loop. Now try to solve the numerical. Fabric with mass per unit area 350 gram per square meter has a flexural rigidity of 20 micronewton meter. If the tip of the fabric has to reach to a point 15 degree below the horizontal plane, then the overhang length we have to calculate. We know the relationship. So mass per unit area is given and flexural rigidity is given. So bending angle is 15 degree, and we have to calculate the overhang length. So from this relationship, G equal to MC cube multiplied by 9.807 multiplied by 10 to the power minus 6. So from this relationship, if we get the value, M value is given and C is the bending length there, and from this relationship we can calculate the bending length here. So bending length is 38.041 millimeter. Okay. And from this relationship, bending length equal to L multiplied by cos theta by 2 by 8 tan theta power 1/3. So from this, so angle is given 15 degree theta. So theta by 2 7.5 degree, 8 tan 15 degree. So here we will get this factor 0.733. Okay, this is 733 bending length, and overhang length is 0.733 is the bending. So this is the factor. This factor is here given. Okay. This is the factor which is calculated separately, and this is function theta. Now overhang length L equal to bending length by function, this function. So bending length is 38.041, which we have calculated here, divided by 0.733, it is coming out to be 49.19. So bending length is 49.19. So overhang length is bending length is first calculated. So overhang length. So this 49.19 is the overhang length, not the bending. Bending length we have calculated is 38.041. Next numerical. Here, fabric with mass per unit area 250 gram per square meter, having flexural rigidity of 250 micronewton meter. If the tip of the specimen has to reach a plane 10 degree below the overhang length, then the overhang length is from the given data. Fabric aerial density is given 250 gram per square meter. Flexural rigidity is 250 micronewton meter. Theta 10 degree. So overhang length we have to calculate. So this G value is given 250. From there we can calculate the bending length C using the given relationship. So C becomes 46.71. Again using another relationship, C and L, that is overhang length relationship, we can calculate the overhang length. So this function theta, which is this one, cos theta by 2 by 8 tan theta, okay, power 1/3. So that we can calculate, which is f theta is becoming 0.89 for the theta 10 degree. Okay, 10 degree below the horizontal plane. So overhang length becomes bending length 46.71 divided by 0.89, it is 52.48 millimeter. Next numerical, a fabric with mass per unit area of 300 gram per square meter. Flexural rigidity is again given 325 micronewton meter, and tip has to reach the plane 14.2 degree below the horizontal plane. In that case, overhang length we have to calculate. So again, the same way, mass per unit area is given, and theta is given, textural rigidity is given. So from the given relationship, we can calculate the bending length. So bending length becomes C 47.98, and the function of theta, that this factor we let us calculate separately, and this becomes for the angle theta 14.2, this function become 0.79, and the overhang length will become 47.98, which is bending length, divided by 0.79, 60.73. So after bending, the next important characteristic is the shear characteristic. Shear is one unique parameter, unique property which the textile material has got. So textile material has got very high tensile strength, but comparatively shear strength, shear rigidity is very low. That's the uniqueness of any textile material, and which helps in the adjusting our fabric shape. If fabric gets complex deformation, and it will adjust to our body contour. So for the same fabric, it actually conforms to our body contour due to the shear characteristics. So it is most important property which determines how a fabric will perform when subjected to wide variety of complex deformation during the use. And shear is measured. It's basically its ability of a fabric to deform by shearing, which differentiate it from other thin sheet material such as paper or plastic. So a very soft paper or very thin plastic film, if we make our garment from very thin plastic film, even if it is porous or soft, still we will find uneasiness during wearing because of the lack of shear deformation. So shear deformation in textile material, where the separate threads are there in warp web threads in woven fabric, in knitted structure, this fabric has got very high shear deformation, which helps in adjusting our changing body posture. So it conforms to the contour of human body. As the textile material is very flexible, so shear deformation measurement is very difficult. For any other material, engineering material, like any metal plate, we can measure the shear deformation. Shear means applying parallel force in the opposite direction, and we try to get the deformation. So textile material being highly flexible material, so measurement is very difficult. So if we see the simple shear, this diagram shows the simple shear mechanism, where ABCD is the initial dimension, and when we apply a force F in opposite direction, parallel force, in that case the fabric gets deformed and it becomes A, B dash, C dash, D, where the angle of deformation is theta. This is the angle of deformation, which is called shear angle. So for simple shear, parallel stress F acting opposite direction, tan theta is shear strain and P is shear, F is shear stress. The shear stress is expressed by the force per unit length of the fabric. If the length of the fabric here is L, so F by L will be the shear stress. And here the assumption is that during shear deformation, the area of fabric doesn't get changed. So ABCD will be equal to AB, C dash, A, B dash, C dash and D. This is the assumption. And shear rigidity is it's a ratio of shear stress by shear strain, F multiplied by G tan theta, where G is the shear rigidity. So shear modulus, G is the shear modulus. In case of textile material, so if this simple shear is possible in case of the stiff material, solid material like a metal plate. Okay, but in case of flexible material like textile material, it is very difficult to deform in this fashion. In normal case, the fabric will get buckled. To eliminate this problem, we apply one normal load. So we hang one load W so that buckling doesn't take place, and then test the shear test in normal one. Okay. So to avoid buckling, a vertical force is applied, which is W. So the extra force required for this W vertical force, extra force for shearing, which is W tan theta. Okay, due to W. So effective shear force is the total shear force minus the shear force required, extra shear force required due to the applied vertical load, which is F tan theta. So F minus W, W tan theta. So F minus W tan theta is the effective shear force, and shear stress is expressed as per the force per unit length. Now let us try to solve this numerical. A woven fabric of dimension 20 centimeter by 20 centimeter is tested for a plane shear characteristics. The total force required to deform the fabric up to 10 degree under a dead weight of 1.3 Newton is 1.6. So shear force, total shear force is 1.6 Newton and dead weight is 1.3 Newton. So let us calculate. So effective shear force is given by this relationship where the F is the total shear force required, W is the dead weight and theta is the angle. So total shear force is given 1.6 Newton, W is 1.3 Newton, theta is 10 degree. So from this we can calculate the effective shear force is, so 1.6 minus 1.3 multiplied by 10 degree, it is become 1.3708 Newton. So that is the effective shear force. And shear modulus, so shear stress is calculated effective shear force by specimen length. So specimen length here 20 centimeter. So it will be in meter. So specimen length is becoming 0.2 meter. So effective shear force divided by specimen length, it will become 6.85 Newton per meter. And shear modulus, we know the relationship shear stress equal to shear modulus by shear strain. So shear modulus is, shear stress is 6.85 and shear strain is 10 degree. So we get the shear modulus 38.9 Newton per meter. Now shear hysteresis is, it occurs, this is due to the frictional force at the interaction point of the warp and weft between the, if it is in the case of woven fabric. So when we apply the shear deformation and after the removal of the load, the material will come back, but there will be some hysteresis. This is mainly due to the frictional force. So initial shear modulus is the slope of the curve at the origin point, and shear modulus at zero shear, okay, that is slope at point B and D. So at point, this is point say B. So here maybe in this, as per this picture, S and Q. So if we calculate the slope at this point and if we calculate the slope at this point, in these 2 points, if we see, so slope at zero shear, so we will get the shear, and initial shear modulus will be slope at the origin point. Hysteresis is the distance between this S and Q. Okay, this will be SQ. Length SQ is the hysteresis. Now shear can also be measured by biased extension. So fabric is cut at 45 degree. So normally in tensile testing we cut the fabric along the yarn direction, warp or wave direction, but in biased extension method we cut the fabric at certain angle. Normally it's a 45 degree for woven fabric. So using this relationship where G is the shear modulus, okay, E1 is the tensile modulus at warp direction, E2 is the tensile modulus in wave direction, and E45 is the tensile modulus at 45 degree angle. So this is the tensile modulus. Where, so from there if we compare that E1 and E2 are much higher than E45. E45 because due to the shear this fabric will extend very easily at lower load. So modulus is very low. So as E1 or E2 are much higher than E45. So these two terms will become very negligible. So simply we can use the relationship as E45 approximately equal to 4G. So these two terms will be neglected. And similarly, the shear strain is approximately equal to 2E plus E square, where E is the biased extension. Okay? And where E is very small because we cannot extend too much. So at very low extension, then only we can measure the shear strain. So as E is very small, so this part square of E can also be eliminated. So tan theta is approximately equal to 2E. And therefore, the force, effective shear force, okay, is equal to approximately, we can calculate, it's F by the, for F force, tensile force, the elongation is, biased elongation is E. So for very small extension, this F force is related in this fashion. So this can be derived. So we are not deriving at this stage. Now our next parameter is the drape. Drape is very important parameter, particularly for apparel and home furnishing. So the term used to describe the way fabric hangs under its own weight. So how good a garment looks in use, during using. So if the drape is good, then the garment will look good. So it differs from fabric to fabric and depends on end use. So it's not that if fabric drapes well, always it will be a better fabric. So depending on the application, sometimes we may need, for certain application, we may need thicker fabric with a lower drape, and other time we can need flexible fabric. So depending on our application, the drape value changes. Okay. So a particular value cannot be classified as either good or bad depending on the application. So drape is a multidirectional property. So the multidirectional curvature formed is dependent on the shear and bending properties. So drape is a mixture of shear and bending property. So drape meter, which is shown here, this is the normal drape meter. This is a fabric specimen with area A1, okay, fabric specimen, and which is placed on a support disc with area A2. And after releasing the fabric, putting the fabric hangs due to its own mass. The fabric hangs and forms like this type of shape. And in drape meter, what we do, we have a light source falling on the draped fabric, we get this shape, and we calculate the total area of the shadowed draped fabric. Okay, A1 is the initial area of the specimen, A2 is the area of the support plate. So you can see A1 is the area of the initial fabric shown by dotted red line, and A2 is the draped fabric area, and A3 is the central circle, which is the support plate. Let us see the animation here. Now the support plate is there, and fabric will be placed on this support plate. The initial area of the specimen is A1, initial area. Now when there is no fabric, okay, light is falling on the support disc and we are getting one shadow. This is the shadow of the support disc. Okay, now we are hanging the fabric on the support disc. Okay, the fabric is, we are hanging, and then we are trying to get shadow of the fabric after draping. So this is the shadow. So we get the total initial area of specimen A1, total area of the support disc, that is A2, and total projected area, shadow area, A3. So drape coefficient is A3 minus A2 divided by A1 minus A2. That is the drape coefficient, okay, which will be typically less than 1. For completely stiff material without any drape, where A3 will be equal to A2. Okay, A3 will be equal to A2. Sorry, A3 will be equal to A1. Okay, so for total initial area is A1 and A3 is the projected area. So A3 will be equal to A1. So A3 and A1 is there. Okay, and A2 is the support disc. So this is the area. So for very stiff fabric, H3 A1 will be there, area of the shadow area and area of the fabric. So A3 A1 are equal. So if we replace here by A1, this will become 1. So in that case, so when for very stiff fabric, the maximum drape possible is 1. Okay, when there is no draping. Now consider that fabric is very flexible. There is no projected area, projected portion. In that case, A3 will be equal to A2. If A3 is becoming A2, then it will become 0. In that case, drape will be 0. So range of drape comes 0 to 1. Initial area, A2 is the area of the support disc and A3 is the total shadow area by draped fabric. That means for very flexible fabric, drape becomes 0 without any projection, and for very stiff fabric, drape becomes 1. So the range is from 0 to 1. So as the fabrics become stiffer, the drape coefficient will increase gradually. Now let us try to do this numerical. In a drape tester, the area of shadow projected of a 50 centimeter diameter fabric specimen placed on a 35 centimeter diameter support plate is 600 centimeter square. That is projected area. That means it's beyond the support plate, the area beyond the support plate. So drape coefficient we have to calculate. Now see, drape coefficient D is calculated by this formula. We have seen A1 is the initial area of specimen. Specimen diameter is given 50 centimeter diameter. We can calculate the area, and support area also we can calculate, where 35 centimeter support plate is given. So we can calculate the area, and shadow area A3, and the 60 centimeter square is the projected area. That means A3 minus A2 is given directly, which is 60 centimeter square. So A1 and A2 we have to calculate. So A1 is pi by 4 d square. So 1962.25 centimeter square. A2 is 961.62 centimeter square, and drape coefficient we get it's 0.5. Next numerical, projected area of a 30 centimeter diameter fabric placed on 20 centimeter diameter supporting plate is 250 centimeter square. So drape coefficient, in the similar way we can calculate the drape coefficient to be 0.637. 0.637 is the drape coefficient. Now the main problem with this drape meter is that the light source which we are projecting, it gets diverged light. So after projecting on the fabric or the plate, what it does, it gets diverged. So actual area we are not getting. So what we have to do, we should have one system where the light is projected on the specimen in parallel beam of light, not the divergent light. So parallel beam, so this is taken care of in the system which is called the acoustic drape meter, where light is projected on a concave parabolic mirror. So this is the light source here, and above which the fabric specimen is placed. This is the fabric specimen and support disc, and above the fabric specimen there is a glass platform on which annular paper is placed. The inner diameter of annular paper ring is equal to the diameter of the support disc. Now when the light is falling on the parabolic mirror, it is getting reflected and parallel beam of light is falling on the fabric specimen, and shadow is created in this fashion. This paper ring, annular paper ring is available. This is the rings are supplied along with the instrument. Okay, and the outer dimension of the fabric is equal to the of the ring is equal to the fabric dimension. Okay, and this shadow is achieved, then we can cut out the shadow portion and take the mask. This is M2 mask. Now from the relationship we can see this total mass of the fabric of the paper M1 is nothing but E1 minus A2. Area of the fabric minus area of the support plate, and the total mass, this is actually its proportion, M is proportional to the area, because the fabric has got a certain mass per unit area, so this will be in proportion. So M2 is proportional to this A3 minus A2. A3 minus A2. So by definition, the drape coefficient is that A3 minus A2 divided by A1 minus A2. So M1 is constant, some constant A1 minus A2. Okay, mass per unit area. So this constant depends on the mass per unit area. So drape coefficient then is nothing but M2 by M1. M1 is the initial mass of the paper ring, annular ring, and then after cutting out this annular ring shadowed portion, then if we take simply we take the ratio of mass. Okay, the shadow that the fabric casts stressed on an annular paper ring, we can simply stress on the glass platform, the paper ring is there, so we can simply trace the shadow and then cut out. Paper mass per unit area is constant, so mass of the whole paper ring and mass of the cutout portion is measured, and we can calculate the drape coefficient. Now let us see the animation here. So light is falling on the parabolic mirror. So divergent light is falling, on the parabolic mirror, and after reflection the light becomes parallel, and the parallel light is actually projected on the draped fabric, and the shadow is generated on the paper ring, so we can cut out. So mass of shadowed portion by total mass of fabric is the drape coefficient. So different diameters of fabrics recommended depending on the drape coefficient range. Okay. Now let us try to do a few numericals. A fabric specimen when tested in QC drape test system result drape coefficient of 0.82 if the inner and outer diameter of the annular paper ring used is 15 centimeter and 35 centimeter respectively. If the areal density of fabric is 10 GSM, 10 GSM fabric, sorry, 100 GSM fabric paper is used, so the mass of the shadowed portion you have to calculate. Drape coefficient is given, so mass of the shadowed portion is X. So area of the paper ring is calculated 0.078539 square meter. So paper ring is outer area, outer diameter is given and inner diameter is given, so that's how we can calculate total area. And paper GSM is given 100, so we can calculate the initial mass of the paper ring. So total mass of the paper ring is at 7.85 gram from the relationship of drape coefficient is the mass of shadow portion and total mass of the paper ring. So mass of shadow portion is required, total mass of the paper ring is 0.82, so 7.8539 and drape coefficient is 0.82 given, so we can calculate the mass of the cutout portion 6.44 gram. Okay. And our last numerical in this session, mechanical characteristic session, is a fabric specimen when tested in QC drape test system that results the drape coefficient of 0.62. If the total mass of the paper ring is 9 gram, the mass of the shadowed portion. So total mass of the paper ring is given. So earlier case we had to calculate the total mass of the paper ring from the area, but here directly it is given, so it will be simpler. So total mass is 9 gram and drape coefficient is given 0.65. So x by 9 is 0.65. So x is 5.85. That is the after cutting the paper ring, so annular paper ring, the mass will be 5.85. So we have come to the end of the session, where we deal detailed the various aspects of my tensile characteristics, low stress mechanical characteristics. So till then, thank you. So in next class we will discuss some other aspects of analytical approach of textile testing. Thank you.